Hey guys, I'm going to be doing my video about problem number 1 and 3 from spectroscopy. I can't say that word. Anyways, first problem is a particular molecule can absorb a photon with just enough energy to excite an electron in a molecule. Monochromatic light bombards a group of these identical molecules, so 3.3 electrovolts of energy is absorbed. Can orange light 600 nanometers have been used? Answer the question by calculating how many orange photons would have been absorbed. So right here we're looking for number of photons. Okay. So for the first one, we're given 3.3 electrovolts, and we're given the wavelength 600 nanometers. And we're looking for the number of photons. So how do we relate energy and wavelengths? We're going to have to go back to chapter 2, section 2.24, which is light, photons, and electromagnetic spectrum. So in here we see the equations for electromagnetic waves, the speed, wavelength, and frequency. And we can see that C equals wavelength times frequency. C is the speed of light, which is 3 times 10 to the 8th meters per second. We're also given another equation, which is the energy of one photon of light. And that equals, the energy of one photon of light equals Planck's constant times frequency. Planck's constant is 6.63 times 10 to the negative 34 joules per second. So what we're going to do is we're going to find an equation where we can relate energy and wavelength. So here we have the energy, or the equation for speed, wavelength, and frequency, and the one for the energy of one photon. Now, we're given wavelength, and we're trying to find energy. Planck's constant is a given, and speed of light is a given. So the only thing that we don't have in these equations is F. So we can pretty much combine these equations to just get rid of F, frequency. So we're going to isolate this to find frequency. Then we're going to plug in this value up here for frequency here. So now we have a new equation. Energy equals Planck's constant times speed of light divided by wavelength. Okay. So now we were given electrovolts, and we need to convert that to an energy unit that we can use, which is energy in joules. So we have this relationship that 1 electrovolts equals 1.6 times 10 to the 19th joules. So we can take the joules, the electrovolts that we were giving, and we can times it by 1.6 times 10 to the 19th joules, and we end up with 5.28 equals 10 to the negative 9 joules. So now that we have all the information we need, we have Planck's constant, we have speed of light, we have the wavelength, we can find energy. So right now we're going to solve for the energy of just one photon. So we have E equals Planck's constant times speed of light divided by the wavelength, and the wavelength we were given was 600 nanometers, but to make the units cancel out we need to convert it to meters, so it's 600 times 10 to the negative 9 meters. Now we're left with 3.315 times 10 to the negative 19th joules, and that's the energy of one photon. Now we just want to find out how many photons absorb the energy. So if we go back here, we have the total energy absorbed, which was from the electrovolts that we found. So we have the energy absorbed divided by the energy of one photon, and that'll give us our number of photons. So we have 5.28 times 10 to the negative 19th joules divided by the value that we just found for the energy of one photon, which is 3.315 times 10 to the negative 9th, and that equals 1.59 photons. Okay, now we're going to move on to problem 3. Problem 3 states, if every molecule in 1 mole of hemoglobin absorbed a photon of light with a wavelength of 660 nanometers, how much energy would be absorbed? As it will be demonstrated in the next section, absorbance depends on several factors, one of which is molar concentration, As an example, for blood, there is around 2.3 times 10 to the negative third moles of hemoglobin per liter. Okay, we're asked to find joules. Now, when we look at this equation at first, or look at this question at first, you notice there's a lot of information here, and this is kind of what we call like a red herring. It's information that we don't need for this problem, but it's just thrown in there, so we're not even going to be using that. So, what we were trying to do is we're trying to see how much energy was absorbed. So first off, we're given that we're trying to relate 1 mole of hemoglobin into the number of photons. So they told us that if every molecule in 1 mole of hemoglobin absorbs 1 photon. So we have 1 mole equals 6.022 times 10 to the 23rd molecules. And if every one of those molecules absorbs a photon, then we just have the equal amount of photons. So we have 6.022 times 10 to the 23rd photons. So now we have the number of photons, which is 6.022 times 10 to the 23rd, and we have the wavelength. So we are looking for the energy that is absorbed. So we're going to use the last equation that we used for the last problem. And it's fairly just plug and chug from here. We're going to use Planck's constant, the speed of light, and then we're going to divide by the wavelength in meters, and we're left with the amount of energy in 1 photon. So our energy in 1 photon is 3.0136 times 10 to the negative 19 joules. Now the total amount of energy absorbed is the amount of photons that we have and the amount of energy per photon. So we're just going to multiply those by each other, and we end up with 181,481 joules. All right, thank you so much.